Depending on where you live on the globe, either today or yesterday was the Pi Day. I am not into number theory and I don't have the expertise or anything. I looked into the saved questions on my Stack Exchange profile to see if there is anything relevant, but I couldn't. However, we know how complex analysis is a fan of the number pi, and I will be teaching a complex analysis course beginning next week. One of the amazing theorems that I recently came to appreciate is Looman-Menchoff theorem. I hope I'm pronouncing that right. It says that if you have a complex valued function on an open set and that is continuous, if further you assume that the partial derivatives exist and satisfy the Cauchy-Riemann equations, then f is holomorphic, that is, f is complex differentiable everywhere in U. This, on a first reading, may seem one of those things you definitely have seen in the first complex analysis course you ever took, but there are delicate questions here. Everyone, of course, hears that, okay, complex differentiable if and only if you have Cauchy-Riemann equations. But here we're not assuming differentiability of the function. We only assume the existence of partial derivatives. Now let me illustrate what is at stake here. You are given this function f, and u and v are its coordinate functions. Component functions rather. Partial derivatives merely mean that u and v on their own separately and individually have partials with respect to x and y. But we often, of course, put them in the matrix form like this. Then the first delicate point is that existence of partials does not imply differentiability in the sense of Frechet of function. Frechet derivative, remember, is claiming that there is a linear map, in this case from R2 to R2, such that the function is approximated by this linear map up to order 1. We have seen this example in some previous video, probably when we were talking about Rademacher's differentiability theorem. You take a sequence of points that converge to the origin along, say, y equal x squared curve. And x is strictly positive, so this set. Now f, let f be 0 on this set, this subset E. Be 1 on this E, and f is 0 on the plane minus E. What happens is that in every direction that you look, you will see only finitely many of these points. In fact, just one of them at most, or none at all. And from that, you can see that partials of u and v are all equal to 0 at the origin. Okay? It's even more even is true, and that is every directional derivative is 0. So all directional derivatives exist. They linearly depend on the direction v you take. Moreover, the Cauchy-Riemann equations hold, as you can see in this case. Yet, f is not differentiable neither in the sense of Frechet nor complex differentiable, because both of those differentiabilities imply that the function is continuous. This function is not even continuous to begin with. But f is not differentiable in either sense at 0, 0. Okay. So what is this thing we have to remember from complex analysis that Cauchy-Riemann implies complex differentiability? That is this lemma. If we know that f as a function, viewed as a function from a subset of R2 to R2, is Frechet differentiable, and partials, if it is Frechet differentiable, definitely partials exist. The reverse is not true. And partials satisfy Cauchy-Riemann equations, then f is complex differentiable at that point. This is a pointwise result, by the way. So to emphasize, I can say at some z, then it's complex differentiable at z, at the level of just 1 point. So the point here is that we begin by assuming that the function is Frechet differentiable, and then in addition it satisfies Cauchy-Riemann, then it is complex differentiable. The reason for this, the proof of this is basically because if it satisfies Cauchy-Riemann equations, this is exactly saying that the matrix is of the form AB negative BA. And these matrices are exactly those matrices, those linear maps that are complex linear. That means they are of the form, in the complex notation, this linear map sends a vector z to w dot, not dot, times z, where w is a fixed complex number. And when you have the derivative that is c-linear, it exactly implies that the function is complex differentiable. Indeed, the complex derivative is then equal just to this w. You can verify this on your own, but that is the proof. If we already know that there is a linear map approximating the function, and moreover it has Cauchy-Riemann, then we know that the linear map upgrades from being linear on the field of R to being linear on the field of complex numbers, and that proves by definition complex differentiability once you write that difference quotient and whatever. Okay, in the theorem we had that partials exist. So is there any result that says that starts just by assuming partials? Yes, this is also famous. So if partials of any function of any f exist and are continuous, then f is Frechet differentiable on U. So if we assume partials are continuous, then existence of partials does imply Frechet. So if we combine these two, you get this result. So the corollary of the two lemmas is that if partials exist, are continuous, one of the lemmas had this assumption, and the other lemma had this assumption, and satisfy Cauchy-Riemann equations, then f is holomorphic. It's complex differentiable everywhere on U. Holomorphic on U. This is just combination. Partials exist and are continuous implies that the function is Frechet differentiable by the second lemma. And then first lemma said that if it is Frechet differentiable and we have Cauchy-Riemann equations, then it is complex differentiable. So just put them back to back and you get this corollary. So what is then this Looman-Menchoff theorem? It says that if partials exist and satisfy Cauchy-Riemann, then F is holomorphic. So what is the subtle point? No assumption on continuity of partials. It just says that they exist and satisfy the Cauchy-Riemann. So in particular, this theorem says that the function, so this theorem in particular, remember, that will imply that F is Frechet differentiable, because complex differentiability is even stronger. So this is one of the cases where existence of partials implies Frechet without upfront assuming their continuity. So what is the replacement, the substitute for that continuity? The Cauchy-Riemann equations. So this is saying that if you assume existence of partials and Cauchy-Riemann, you don't need to further assume that they are continuous for F to be Frechet differentiable. And from the lemma we had, if you know from these assumptions, if you prove that F is Frechet differentiable, then you're done actually, because we saw that Frechet plus Cauchy-Riemann easily implies by just linear algebra that the function is holomorphic. Another small thing here that you may not pay too much attention to is that why begin with F continuous? Because you're assuming that partials exist. Doesn't that imply continuity of F? No, I just gave you the example. A function, not only partials, but all directional derivatives exist, the function is still not continuous. And then there is a more complicated example on the Wikipedia page, not complicated, I mean a different example, where an even nicer function is built where existence of partials does not necessarily imply continuity of the function. So there you go. This is one of those theorems that is just so so beautiful. It's one of those reasons. It's one of those theorems that reminds you why we love math and takes us back to the roots and classics. This is so satisfying, just because you know partials exist and the Cauchy-Riemann hold. You get such strong conclusions. Remember that holomorphic functions are infinitely many times differentiable. U and V are harmonic. The function is analytic. It has a power series representation, and so many more facts we know about holomorphic functions all of a sudden kick in here. For example, from this indirectly, you get that if you have a continuous function with partial derivatives that satisfy Cauchy-Riemann, then that function is infinitely often differentiable. And that's just beautiful. I hope you enjoyed this special for Pi Day, although there was no pi. Well, maybe let's put pi here so there is a pi. And hope to see you in future videos, not necessarily about complex analysis. At some point, I want to talk about the course I'm teaching because I'm so excited about it, and I have written some notes that I will share. But until then, thank you so much. I wonder who will be the 400th people subscribing to the channel. See you soon.